Cultural significance. Stars have influenced human culture, religion, and science, inspiring awe with their beauty and ubiquity. Numbers and scale. The universe contains an estimated 300 sextillion stars, with 200 to 400 billion in our galaxy, the Milky Way. How stars work. Stars are massive spheres of plasma, essentially continuous nuclear explosions held together by gravity. Energy source. Powered by nuclear fusion, stars primarily convert hydrogen into helium, releasing immense heat and light. Solar mass. The Sun's mass, 1.989 times 10 superscript 3 kg, is used as a benchmark to measure other celestial bodies. Formation of star. Molecular clouds. Dense clouds of hydrogen, helium, and dust form in space. Protostar stage. Collapsing clouds heat up due to gravity, creating a core that eventually ignites fusion. Main sequence stage. Stars spend 90% of their lives fusing hydrogen into helium, radiating energy. Life cycle of stars. Small stars, red dwarfs, burn fuel efficiently, lasting up to 1 trillion years. Medium stars, like the Sun, enter a red giant phase after hydrogen depletion, expanding dramatically. Massive stars form supergiants or hypergiants, emitting intense radiation and eventually ending in spectacular events like supernovae. Gigantic stars. Scuti, among the largest known stars, with a radius 1,700 times that of the Sun. Its enormity is awe-inspiring. If placed in our solar system, it would engulf Saturn. The death of stars. Low-mass stars collapse into white dwarfs after exhausting their nuclear fuel. High-mass stars may end as neutron stars or black holes, depending on their initial mass. So, there's a slim chance that you, watching this video, may be able to witness Betelgeuse going supernova and outshining the rest of the galaxy in our lifetimes. As for when it will happen, well, we simply cannot tell. After the brilliant visual display of the supernova has occurred, the cores of these stars can still continue to evolve. In some cases, the core will collapse in on itself and form a very dense, comparatively minuscule object with an immense gravitational field relative to its size, known as a neutron star. What was once a massive star capable of engulfing millions of kilometers collapses in on itself to form an object no more than 30 kilometers wide. In some cases, these celestial bodies will rotate rapidly and sometimes emit beams of radiation detectable from Earth, called pulsars. It was through this pulsar phenomenon that, in 1967, a signal named LGM-1 was discovered, a radio signal from a pulsar that was initially attributed to a transmission from an alien civilization. Most neutron stars have such strong gravity fields that if you were to drop a teaspoon from shoulder height to the ground while standing on one, the spoon would reach speeds in excess of 22,000 kilometers per hour before it collided with the ground. However, that still isn't the most extreme thing massive dying stars can form. Not all post-supernova stars collapse to form a dense neutron star, some take it a step further. If the stripped-back core in question is in excess of 4 times the mass of the Sun, then the resulting force of the implosion will be so great that it will compress the entire core into a single microscopic point with near-infinite density, known as a singularity. The resulting gravity field is so strong that past a certain point, not even light can escape. The massive collapsing star has now formed a black hole. Black holes are some of the strangest things in the universe and are the ultimate all-consuming eventuality for the most massive stars. While these black holes aren't usually the supermassive black holes at the centers of galaxies, they can still achieve some pretty impressive sizes. Whatever happens to a star when it dies, it's never usually boring. So, there you have it. We've now covered the life cycle of a star, from its formation to its death. These massive thermonuclear explosions are responsible for shaping so much of the universe you see around you. While galaxies are the legions of the cosmos, stars are the centurions. But the question is there a size limit that stars cannot exceed? Well, theoretically, yes, there should be a size limit for stars, and this is not due to the mechanics of the star itself, but more to do with the star-forming molecular clouds. These clouds cannot exceed a certain mass when incubating stars, or they would lose their star-forming properties. With this in mind, some papers have speculated that the upper bound for stars should be about 150 solar masses. But then again, we've discovered stars such as the blue hypergiant Pistol star, which are estimated to be closer to 200 solar masses. So, no one really knows for sure. Ultimately, we can conclude on an upper bound limit for mass, but when it comes to size, there are a few more variable factors. The largest known star is about 1,700 times the diameter of the Sun, and some predict that cool supergiant stars could grow to as big as 2,600 times the Sun's size, but others dispute this. Principally, there is no absolute cutoff point that we can set as a benchmark, because we simply don't know enough about the detailed long-term process of star formation and evolution. And who's to say that in the future, an abnormal star won't be formed which is greater than any other star that has ever existed? The idea of an upper size limit hinges on the assumption that the number isn't fluid, but we simply don't know. Even a survey sample of an entire galaxy doesn't really provide the clear picture we need to gauge a better understanding of star metrics. However, every discovery we make challenges old ideas, and so the only way we can ever conclude on star size limits is to continue to discover, observe, and research these giants of creation. Stars are truly some of the most wonderful things in the universe. With our wealth of knowledge now, it's easy to lose sight of them as we think bigger, galaxies, galaxy clusters, and the rest of the universe. But when you break a galaxy down to its key component, you see the root cause of so many defining features of our universe, all because gravity attracts hydrogen and helium atoms together, and given enough time, complex processes produce these brilliant stellar firework displays. From the dwarfs right up to the hypergiants, each star has its own story to tell, its own solar system, and its own possibilities for supporting life. With 306 trillion stars out there and hundreds of sextillion more beyond the boundary of the observable universe, the possibilities really are endless.